Hello, and welcome to Summarize Science. Teaching a robot to do something simple for us, like use a screwdriver, is incredibly difficult. A big reason why is the sim-to-real gap, the massive difference between a clean computer simulation and the messy, unpredictable real world. But researchers at UC Berkeley have developed a fascinating new framework called DexScrew that cleverly bridges this gap. Their approach starts with a counterintuitive idea: don't even try to make a perfect simulation. Perfectly simulating the physics of screw threads or the feeling of touch is extremely complex and slow. Instead, they trained a robot hand in a vastly simplified simulation. As you can see here, they replaced the complex screw with a simple rotating joint, just to teach the robot's fingers the basic twisting motion. Once the robot learned this basic twist skill, they brought it into the real world for phase 2. Here, a human operator uses a VR controller to guide the robot's arm, getting it into the right position. Instead of controlling each individual finger, which is very hard, the operator just presses a button to activate the twist skill learned in simulation. This lets them easily collect a lot of high-quality data of the robot performing the task in the real world. This brings us to the final and most important step. While the human was guiding it, the robot was recording everything, especially the rich data coming from its pressure-sensitive fingertips. This real-world data, full of complex contact dynamics and tactile feelings, was then used to train a final, master policy. This new policy learns to coordinate both the arm and fingers together, using the sense of touch to make fine adjustments. So, how well did it work? The results are impressive. The robot could successfully fasten different types of nuts, including hexagonal and cross-shaped ones it had never seen during training. This table shows a crucial finding. Performance jumped dramatically when the robot could use tactile information and a memory of its recent movements. Without the ability to feel the nut, the robot often failed, but with touch, its success rate soared to nearly 100% on some objects. The final policy wasn't just accurate, it was also robust. In this demonstration, you can see the researchers actively disturbing the robot by dragging its fingers away or twisting the screwdriver in the wrong direction. Remarkably, the robot consistently recovers and gets back to the task, showing it has learned a truly stable skill. So let's recap the brilliant strategy here. First, learn a course, foundational skill in a cheap, imperfect simulation. Second, use that skill as a tool to help a human operator easily collect rich, multi-sensory data in the real world. And third, train a final, robust policy on that real-world data. This simulation-to-teleoperation to final policy pipeline is a powerful way to sidestep the hardest parts of both pure simulation and pure real-world learning. This kind of approach could be key to creating robots that can perform complex assembly and manipulation tasks in factories, and maybe one day, even our homes. Thanks for watching Summarize Science.